Ladies and gentlemen, I wish you a very warm welcome to the release webinar for SimulationX 2025. It is the newest release and it just came out in August, and I would like to show you what kind of new capabilities and features we have implemented in this offer. My name is Andreas Abel and I'm the product manager for SimulationX. Before I enter into the product demonstration, I also would like to comment on a few changes which we have seen for SimulationX in recent days. You might have noticed that the ESI group was acquired by Keysight Technologies, so SimulationX is now part of the Keysight software portfolio. This led to some reorientation or refocusing with our products. So we now look much more strongly into our network of partners throughout the different regions in the world. Apart from that, you will see that there is a little bit of change coming on the branding side. We have a new icon. We also have new branding colors, but apart from that, nothing changes from the product, as you know, and we just strive at delivering even better experience and excellence than you have known before. Thanks also to the partners. Now, let's have a look in what is new in the context of libraries and functions in SimulationX. We have improved various libraries, various components. I would like to put a little bit of focus here in my presentation today, so I will look into what we changed now, battery library, how we improved the heat exchangers, how we now added capabilities into drivability analysis of vehicles by adding an ESP controller. There are changes in the driving maneuvers, road import modeling, and we have some changes on ship energy systems, which I also would like to touch in the end of this section of the presentation. So let's start with the battery libraries. There are two main changes or additions which I would like to mention here. The first one is battery aging. Battery aging looks into the long-term impact of how you treat your battery, how you run your battery, and how this will degrade the performance characteristics and capacity of the battery. This typically happens through the usage of the battery, so this is called cyclic aging. So the permanent charging, recharging of the battery leads to changes in performance, degradation in performance. But there are also chemical degradations observed in the battery, which let the battery age and lose performance over time just from not being used sitting on the shelf. In practice, we observe that these two effects here on the batteries are appearing in combination. If you want to learn a little bit of what we have implemented on the aging in the batteries, then I can recommend you to have a look on the online help for the SimulationX battery models. And here you find the quite extensive description of what kind of approaches like an Arrhenius equation for calendric aging has been implemented in how we met this into the changes of battery characteristics. I don't want to dive too deep into this aspect. Of course, it's good to have a nice and concise online help, but I would like to show you a little bit of that on a simulation model. In order to demonstrate that, I have picked a model of a motorcycle, an electric motorcycle. So we find typical components like the batteries coming from the library. We have an electric motor, and we have a motorcycle driving resistance model, which allows us to consider air drag, hill inclination, as well as the driving or rolling resistance coming from the tires. Mechanically, this model is pretty simple because the attention here is really to look into aging, which means we need to look on long time intervals, like number of days or even a whole year, as this model is doing. In order to run that, we also need to specify how this motorcycle is driven when it is charged and how long I want to operate it over a day, how often I want to charge. This is all part of the control elements, which we see here, generally driving control, but also a control here down in the model for battery charging. I will start the simulation. You will see it's quite fast. So I would like to just show you here the first part of the simulation run to explain a little bit what kind of cycle we model. You see here on the top a speed profile. So it starts somewhere at 7:00 in the morning, and then we go for a while. It's about 20 kilometers with a mix of city driving and cross-country driving, apparently. And then in the evening at 3 or 4 p.m., I pretty much revert the same cycle. So I go back home. It's a typical commuting scenario. And during this commuting scenario, we see that we start with some level of battery charge, 80% here in this case. Then I use some of my battery charge in order to drive to work. Then the vehicle is just sitting around. I drive again. I go down to a level of about 60%, 75% battery charge. And then in the evening, when I come back home, I plug in the motorcycle And then with a plug-in motorcycle, I recharge to pretty much the same target level where I started, which is 80%. Of course, if I would observe this through just one day, I will not see any significant changes along my battery. But when I go and say, okay, I do this over a whole year, then I certainly will get into situations where I see a change of battery characteristics. And this is what I see here in my second diagram. Meanwhile, the simulation has been finished, and the curve which we generated about the battery capacity is the red one. And you see that through the usage of the battery, we actually see that the capacity of the battery slowly decrease. When we take a close look here, we also see that I use this model to record a variety of scenarios by parameterization. The aging characteristics here in the battery, if I look inside, I will see that there's a possibility to select what type of aging I want to use. It can be a combination of calendar and cyclic aging. It can be either one, and it can also be simulated without aging. So just with a set of parameters, which I specify for this specific chemistry, and these are the 4 situations which I also see here at this chart. So the green line on top is just the simulation with no aging. The red line underneath is the simulation with only cyclic aging. The blue line is only calendar aging. So I didn't use my motorcycle for a year, which is not the smartest idea. And the red line on the bottom is the simulation which I just run, and it shows me the combination of both aging mechanisms. This gives me a good way to understand aging, analyze it in operating scenario as I do here. Of course, I can use more complex driving or charging scenarios. I might want to incorporate weather conditions. All this is not here part of the sample model, but it's something which is easily possible in SimulationX. And as you have seen, it's pretty fast. So it was completing a whole year of simulation in the time where I was just explaining the model. Let me go back to my presentation and mention a second aspect which we implemented in the battery library, and this is dynamic behavior. What is the meaning of dynamic behavior? Dynamic behavior expresses what the battery is doing when it's charged and discharged. In an ideal world or ideal assumption, you just go from one battery charging level to another. One level of voltage, open circuit voltage in the battery. But in reality, we will see that the battery has a dynamic response. So it's actually like filtering and processing the way how you're charging, and it will come with a certain delay in responding to that. And these delays are associated different mechanisms. So if you run through a charging cycle, you will see that with these mechanisms, actually the open circuit voltage will not follow as quickly as you charge the battery. And even if you stop charging, you will see that there is certain separation effect. And this is what is shown here in a discharging charging cycle. It's just a segment that is coming from another example model which we provide with the battery. And there you see it, this result graph that the battery is charging, then it's discharging, charging again, charging, discharging. In reality, the open circuit voltage on a cell will actually follow with a certain delay in gradient to this kind of input which I generated here. Well, another aspect which is worthwhile to be mentioned, coming back to my model here, I spoke about already that we simulate quite fast, and I managed to run a simulation for a 1-year model time in just a few minutes. And one reason for that is that we also spent some effort in optimizing our models of stacks, which usually are combined by a larger number of cells. So in this case, here in my motorcycle model, I will see that the stack model has 142 cells in serial and 4 of those packs in parallel. And if I just model this as individual cells, one thing I will see that the model complexity, it's quite quickly growing and exploding, which means I will have to pay a penalty in symbolic analysis, in compilation time, in the number of states, and eventually in simulation time. And if I use some clever approaches to write this down, like a concatenated matrix equations, then I can drastically reduce the effort. So instead of using every single state and every single equation, I put matrix equations, I put vectors, and as a result, I get a significant acceleration in simulation. So you see here the comparison. First line at the table is before the change with, like, say, the straightforward way of modeling. If you use an optimized way of modeling, then you can actually see that we get something like 20 times faster in simulation times. And this is quite significant. If I talk about running a year, it's a difference if it's 1 minute or 20 minutes, which I have to simulate. And of course, this gives me better flexibility in examining more variants and case studies, which I want to analyze when designing my system. So much for the battery. I would now like to switch to a second topic, and this is about heat exchanger. It's a bigger topic we work on, so you will see that we have already released some of the improvements, some of the changes. There are more to come. And the general goal which we have here is that we want to improve the usability, the simplicity of usage, also for, let's say, non-super experts. Performance is a critical point, as well as numerical stability. And so we started to implement heat exchangers pretty much from scratch and incorporating capabilities like a better studying and separation in there for gas and liquids, but also mixtures and two-phase fluids, so that we better can represent the performance of the heat exchanger. We have added fluids. So you might have noticed that we started to use cool prop fluids in the thermal domain already in the 2024 release. Now we moved into fluids from cool prop also being used in the hydraulics and pneumatics library. So generally what we have achieved already, that there is now a good choice between the kind of model which you want to pick for your application. So it might be a simplified model which gives you like a high-level concept phase approach, maybe not expert approach into modeling heat exchangers. And on the other side, we, of course, want to be able to model very discrete or very detailed and discretized heat exchanger where we control all aspects, the level of approximation, the level of the degree of details. I would like to give you just a quick glimpse on those kind of things. So I again have prepared a simulation model here for an annual heat exchanger. So it actually shows concentric arrangements with having a gas flow and the lighter blue part and a liquid flow for cooling in the inner part. So this is the cross section of the heat exchanger. It's like from the outside, it just looks like a tube. And here, these two liquids are hydrogen on one side. So this light blue on, and in the model circuit you see here, and hydrogen supply going into the heat exchanger system on the lower end. The liquid which is used for cooling is water. And so the idea is here to get the hydrogen temperature down from a certain level and the inlet to another level on the outlet. The application use case behind that is the cooling of hydrogen and hydrogen production plants. So it comes out usually quite warm or hot. And then before it goes to storage, it actually should be cooled down to a certain lower level temperature. So the interesting bit I'm talking about here is this heat exchanger element in the middle. And if I take a quick glimpse on the parameters, I see that this is actually a representation of the simple way of modeling the heat exchangers, because instead of having complex concentration of what kind of geometry what is the shape of the individual components of the different sections of the heat exchanger? What I do here is I specify actually the heat transfer area of the heat exchanger. I specify what's the length of the channels which I have, and I specify what's the cross section of the hydraulic diameter. So this gives me the flow characteristics. Through the heat transfer area, I can specify what kind of heat transfer characteristics I have. And through that, I'm able to use very small information in order to describe the performance of the heat exchanger. And I will also be able to tune this kind of information before I have a specific finalized design. So I might go and say, okay, what is the needed area for the heat transfer in such heat exchanger? And this gives me internal conclusions about how I should dimension the device in the end. What I also can do is I can change the discretization along the heat exchanger. So here it said that over the whole length of the elements, we define 6 segments. So this gives us a possibility in the simulation to reach a higher accuracy, because we now can look at all the fluid characteristics, pressures, temperatures, etc. in each of the segments. So we will see what kind of temperature gradient is developing inside the heat exchanger. And the more accurate I want to be with that, the more segments I could introduce here into the simulation. So if I run that, just to show you, it's again a model which is not very slow here in execution. Then I will see the process, which I just have explained about cooling down the hydrogen. I will see how this goes from an initial state where I have an outlet temperature of 80 degrees C into a control state where I manage to maintain a level of 30 degrees C outlet temperature. And as a result, of course, this controller steers certain aspects of the process. So for instance, it shows here the control wall. It's the amount of water flow which I need in order to achieve these temperature levels. In the beginning, apparently with high temperatures, I should have a big water flow. Here you can see it's saturated, so the valve is fully open. But then when I come to my target temperature, the valve gradually is closed, and I go to a certain level settings to allow the flow of water, which is necessary to get the hydrogen temperature from 80 degrees to 30 degrees. Okay, so moving back into my presentation and switching topics, I now go into driving of vehicles, and there are a few interesting developments. Maybe the most interesting one is the introduction of an ESP controller into SimulationX. It is part of the hydraulic brake systems, and it is a very generic way of modeling controller. So it's not like a specific device which would purchase or which is belonging to a certain type of vehicle or manufacturer, but it's an implementation of the generic functions which you would expect from an ESP controller. So that means monitoring the vehicle and providing input in terms of brake torques to the wheels so that we know where we want to or how we want to control our vehicle. So that's a little bit illustrated here. Again, it's a sample model. It's a model which comes with SimulationX, so accessible for everyone. Everyone has the possibility to play with it. And here, repeating again, we look at vehicle characteristics, very generic characteristic like HR rate, a slip ankle, and then we calculate the required brake torques towards the wheels. But we also have an operating mode where instead of brake torques, we calculate the hydraulic pressures to apply to the brakes. So this gives us an option to introduce scalability. The model we see here in the screenshot is actually just one which is using friction elements in representation of the brakes. So it's very strongly focusing on the dynamics of the vehicle, not so much on the internal structure of component, the braking system. But I could exchange this with a more detailed braking system using the same controller and providing it with hydraulic pressures instead of brake torques. That's again something which I would like to show you in action. So I just need to see where my model window for that is. It's here. And here you see the same model. And the scenario here is that we actually have a double lane change. So the vehicle starts to drive, and then there will be an obstacle. It has to change its strike to the neighboring lane, and then it's supposed to go back. I'm driving quite fast here. So it's 60 kilometers per hour, and this might become a challenge. And I have pre-computed the first simulation. So I just want to mention that what we see now is not simulation, but animation of the results. No, I forgot to pre-compute, so we will watch the results. Sorry for that. If I run the simulation, you will see how the weaker gain speed. You might observe here down in the bottom right corner, the simulation time. You will recognize that it's a little bit slower than real time. That's why I would have preferred the animation to show what's happening. But now you see I come into scenario, a weak obstacles appearing. We see it's a cow, might happen on a country road. And then the vehicle tries, or the driver tries to circumvent the obstacles. It manages to circumvent the obstacle, but increasingly you can see that driver is losing control over the vehicle. And so it starts to skid and it starts to lose direction. And this is, of course, not the situation we want to be. So for this reason, we have ESP controllers. And in the first simulation, as I said, ESP was off. And now just to show you the difference and the impact, and also to show you how simple it is to work with this. I switched the ESP controller on now, so I changed the mode here to true. Of course, I should have some reasonable control parameters. This is something which I do not try to tune. Now it's pre-configured, and it comes here with a model setting, which is matching the vehicle. And then if I go back and do the same experiment again, then I will have to recompile my simulation because it's quite significant change having or not having ESP controllers. So the equation system is different, which means we see another symbolic analysis at the start of the simulation. But then it will be over in some seconds, and then we can observe the same scenario again, where we will see that the car should now behave much better, even at this high speed. Of course, there are other parameters I can play with, so I can play with the difference in driving speeds. And this is something which I did to provoke actually this very nasty misbehavior we have seen in the first simulation. So when you take the original model, it's actually set to 50 kilometers per hour and behaving much more nicely. But this is exactly the kind of scenario which I want to observe, because Here I will see the difference whether I approach with 50 or 60, and the boundary line between the control of a car and no more control of the car might be quite a thin one. So here we are in the same situation. So we actually see that the response also is a little bit slower because the controller sees the very quick steering input and tries to mitigate this a little bit. But then towards the end of the maneuver, we now see that it's much better keeping the prescribed track. So it's following the green line here, and especially it's not getting out of control. And this, of course, what we want to have, and this is why we apply ESP systems to cars. Here we have a possibility to apply this very early in conceptual stage with not a completely designed ESP controller, but through that we give component manufacturers, component suppliers, the possibility to tune system on specific vehicle characteristics. Okay. Moving to another topic, it's still about driving. You know that we have a library for driving maneuvers, which provides different types of vehicle models, different types of tire models. So it is part of the simulation. I just have demonstrated before the vehicle model was coming from this library, tire characteristics were coming from this library. But of course, not always I have a scenario where the ground is nice, and even as I've seen in simulation before. But I would be rather on a road with potholes, or I might even go into a terrain where if I model something like an excavator or construction machinery. So under such circumstances, I have an interest to have a road surface model which has potholes, which has unevenness, so that I can also look how the vehicle or how my subsystem, who are supposed to mitigate road impact, how they would be behaving. And of course, the big question here is, where do I get raw data from? And there's a very well-defined way of describing roads. It's called the curve regular grid, coming in a file with an ending CRG, which we see here. And this is something which we have added to SimulationX capability to import CRG files directly into our different wheel types. So that means curve-based wheel is the one which we have in our library. It's the Keysight provided one. Beside that, we have SimCenter tire from Siemens and Cosen, which also provide, both are able to use CRG, and we use this capability to add a road visualization to these tires. So instead of just having it on a visible road with the profiles, we can use the same CRG file to visualize what the vehicle's doing. This is a topic where we are not yet finished. We are also looking into how to extend these capabilities, and more plan we have is to build what we call prototypically a road creator, where you can actually design your roads, building segments, defining curves, defining road surfaces, and then generating CRG file on one side, and on the other side also being able to directly supply the road surface into the different tire models and the road visualization models, as we do right now already with the CRG files. Okay, so this was a lot about mainstream activities, mainstream libraries. We also have some applications which are less widespread, but nevertheless as interesting as the other ones. And one of them is ship energy systems. So this is a library which is already around for a while, but we applied a change here by saying, well, we need to get it into modern times. And in modern times, when you look into ship propulsion, an important aspect is that people start use more and more fuels which are less environmentally friendly, which generate less pollution, and there is an increasing amount of regulations also around that, penalties if you have a large amount of exhaust pollutants. So there is a strong drive among shipbuilders and system suppliers to go to alternative fuels like LNG, liquefied natural gas, or ammonia, which generate less pollution if you use such fuel systems. Of course, it has a overall impact on the energy management on the ship, so you need to store it somewhere. And contrary to like heavy fuel oil, you also store it in a compressed and cooled way. So that means you need to supply energy for cooling. You need to have a cooling system in your energy management considered, and you also need to transfer the state of the fluid because it comes from liquid from the tank. But if you want to burn it in your combustion engine, it needs to be in gas state. So that means there are vaporizers where you look into, and these are, again, using energy and need to be controlled and monitored. And this is the purpose of our extensions to this ship energy system library. So we have new fluids, we have additional coolants which are used in these circumstances. We have introduced two-phase fluids into ship energy system modeling in order to address this two-phase scenario. the change from liquid to gas state, and all this I mentioned before. CoolProp also here, we use CoolProp Fluid in order to implement this for the ship energy systems library. Well, in addition to that, of course, the capability of modeling fuel systems is requiring essential new components so that we can, what we see here in the circuit, we can model the respective pumps, compressors, vaporizers, etc., heat exchangers, which I use. So this is essential if I want to target such systems and make it part of my overall ship energy balance analysis. This concludes the topics about the libraries. I now would like to go into other more tool-related topic, and the very important for us is the capability to export C code from SimulationX. That's, of course, something which is around for a while, for many, many years, actually. But here we need to advance. We need to capture new capabilities, new opportunities where it can be used. And I would like to introduce a few of changes related to that, which we introduced in SimulationX 2025. So I will talk here about a new license model for exporting FMI specifically from SimulationX. I will show you how we updated our code export workflows and how we also streamline those workflows to create capabilities to easily export and re-import models out of SimulationX, and I will show an example on that. And we also give you some reasoning around that or why we are doing this. FMI export, we have introduced a new license model. Before I talk about that, I would like to introduce, for those who don't know, what is FMI Functional Mockup Interface. It is an industry standard which started about 15 years ago and is meant to support the exchange of simulation models through a standardized API and through this removing obstacles which in the old times existed between different tools. And it has become very popular, very established in various industries. So we now see more than 250 simulation tools supporting FMI. So that means it becomes or is already a very, very essential contributor to how customers use SimulationX in their everyday work. And for us, this is very crucial, apparently. So that means we have been part of this movement definition of FMI and the implementation of FMI from the very beginning. And of course, we are continuing to be on the forefront on how FMI is developed and handled in SimulationX. Speaking about license models, when we look back into the previous release, SimulationX had two options of doing code export. One option was very inexpensive, only requiring 2 tokens supporting all the targets which we have in SimulationX. But due to the limit of 2 tokens, it had a constraint that it was not exporting the source code and it was requiring a runtime license for execution. So that is the price to pay for the low token consumption, and the intention here is to support occasional use, to support single users which take their exported code like FMI or FMU into other applications and using tokens also for the runtime license. On the upper end of our code export spectrum, there is the export which runs without constraints. So it supports all our targets, including FMI. It provides a source codes with the export, and it does not require a runtime license. The price tag for that is 15 tokens, which of course may be quite significant and may be beyond the capabilities of some individual users. So there was an increasing demand to do something, especially about FMI, and to enable an easier use, a better distribution. And the main, let's say, limiting factor of a distribution of FMU is, of course, if it comes with a runtime license. So here, removing the runtime license greatly increases the capabilities of a user to share his work. That's why we decided we should have this middle level here, which is FMI could export without source code still, because otherwise we would replicate the complete functionality of the big code export options. But here we deliver the binaries, we remove the runtime license, and we enable this feature for 5 tokens. And of course, because it's a token feature, it's something which you do not have to license individually. But you can use it from your token pool, and you can also return 2 tokens back to the pool once you have finished your export. This, by the way, is also true for all of these options. So you don't have to have 15 tokens sitting around if you wanted to code export. We just draw and return them as long as you want to use them. Last but not least, importing FMI into SimulationX always comes for free. Here, let me now move to a little bit of example explaining things around code export, because there's the FMI licensing is one aspect, but there are also other aspects which I would like to bring to your attention. And one immediate thing which you will notice in SimulationX is that we reworked our code export accessibility by introducing a specific ribbon bar for code export. So this ribbon bar as the known options executable model as function FMI, so nothing strange about it. It also supports the import of FMUs. But the new aspect which we introduced here are those two buttons which are currently still in gray, and they help to work more nicely, more streamlined with generation of exported models. So what we now can do is, for instance, here just selecting a portion of some model, and then you see these two buttons get enabled, and I will have the possibility to export this section of a model into different targets, let it be FMU, and I also have the possibility to export this section and re-import the FMU immediately. So this also is a use case which might make sense if I, for instance, want to design or help a control engineer by providing a physical plant model. In such case, I would pick the physical plant, separate it from the controls which I use from testing inside my model. And then I just export this portion. And instead of removing the unneeded portion from the model for export, I now can export a submodel, which makes it much more convenient, and I re-import the FMU here. I also can do some testing. I can see if it works properly. I can see if it connects to my simple control here properly before I deliver it to my partner engineer who is building the controls. This is something which I just would quickly like to illustrate how it works here on this example. So I go for export and replace the FMU. I actually get a warning through the process, which is saying, oh, you have referenced some parameter inside the FMU for your modeling. And of course, I need to change the model in order to address this, because this parameter will be hidden from the surface and part of the C code. And I have to remember that I take this case into consideration here when generating my export model. So what's happening here is now in the first step, very similar to the SimulationX type designer, because what I need to do here, I need to specify a new object. I need to name this new object. I need to specify the IO. So exactly the same what I would do with type designer. So the first pages are pretty much the same as there. And I will also use some of those in order to collect some parameters like properties of my mechanical mass. The displacement, speed, and acceleration of this mass. And I remember that I was warned about the missing information. So for this, I just pick this parameter and make it accessible from the outside so that I can mitigate this problem which I've seen here. So then I continue, and the next steps which I see will take me into the code export configuration. I will have to specify the target path. I will have to specify the type of FMU. Not touching this here because I just want to quickly show how the process works. Everything else is pretty much similar to what I have done in code in the type designer windows already. And so I go here and say, now please generate and build this FMU. And now it's doing exactly this. It is compiling. And once I finished here, I will get it re-imported into my simulation model, and we'll see it appear in my model environment connected to the controller through the interfaces which were already existing. So I didn't need to specify the ports which actually connect my FMU model with the surrounding environment. So I have it here. I still need to correct my mistake here before I can run the simulation. So here I should not use sensor xmax, but I should use my new compound model .xmax. And this should bring me now to a running simulation. I froze the results of review simulation, and hopefully I now see the simulation repeated. One thing I have to look into is that I started to miss here the displacement from my output. I lost the result quantity, so I will just regenerate it here. And then I can observe that I would see the same type of output as in my stored results. So if I take this over here, it will probably not be a perfect overlay in this case. Or I should actually also wait for the simulation to finish. This is mainly because one scale here is in percentage. The other one, which I have available, is in millimeters. And I probably should have picked the sensor reading for a better comparison, as well as the output quantities of my FMU, but apparently something I forgot. But what you would see is actually, it's, well, pretty much similar to the blue case. And that's, I lose it. That's a pity. Yes, I lost it. So this sometimes happened. That's the result of demonstrating things live. So I've crashed my simulation. Sorry about that. This is just illustrating this once again on the slide. We have all seen this in demonstration. I don't need to comment more on that, and this shall conclude my section on the code export. So we have seen that we have a new licensing way for FMIs. We have seen that we have an update export workflow here. More possibilities, more flexibilities, more streamlining. And we also see that we export and re-import of model portions very easily. Last part for the webinar, I would like to give a few quick comments on changes which we have made in order to boost flexibility of SimulationX, and this is namely the SimulationX API or SX API and command line versions which we distribute with SimulationX now. Semla licensing. What is SimulationX command line? SimulationX command line is essentially the whole SimulationX without its user interface. And it's, as the name says, can be run from a command line. So it's supporting batch simulations and integrating into scripting. For instance, it can be used for powers execution with several instances. The communication to this command line version of SimulationX is coming through command line commands and text files. These text files are given through the command line options when you start it. And of course, it comes with a license, but the license is not a fully blown one of all SimulationX, but it's the license of the analyzer edition or the respective number of tokens for an analyzer edition, which is focus. So again, it makes automation nice. It makes batch computation very nice. The other part work to be mentioned is Semla licensing. What is Semla license? It is a standard developed in the Modelica community. You find a link down here at the bottom of this slide to a GitHub resource where all information is collected. And Semla detaches the licensing from the underlying tool. And by this, it gives an opportunity and possibility for developers to introduce their own licensing to a library and to decouple their business completely from the tools, and also make it portable from tool to tool, because the more tools Selma support, the more Modelica libraries can be ported from one to the other tool without changing the licensing on the SimulationX side. We think this is a very nice feature. It is very supportive of community efforts, and that's why we also decided to introduce several licensing into SimulationX, so we now can open and run such libraries coming from other packages. We still have a little bit of work to do when it comes to providing the encryption possibilities inside SimulationX itself, but this is something which we envisage for SimulationX 2026. This already takes me to the end of this small section, and here I would like to say also thank you for listening to this webinar and for watching it. I would like to say, if you have questions, feel free, of course, to get back to us or get back to our partners, and we are very glad to answer and help you on that. Thank you very much.